All right, we're going to go through these reactions from the problem set where you're asked to treat butanol under a variety of different conditions and predict the product that you get. And this problem is just designed to show how versatile a single reactant can be when treated to different reagents. All right, so in this first one, we have butanol. We're reacting that with a base, hydroxide, and formaldehyde. So when you add a base to this, that base is going to deprotonate one of these alpha protons, and that will give you the enolate. And I'm going to draw the enolate where the negative is just on the carbon. Then this will react with formaldehyde, which doesn't have any alpha protons. So this formaldehyde has to be the electrophile. That will add. Here's our new bond. And then we just have our carbon with O minus. And we still have the 2 hydrogen there that you don't have to draw in. From here, because we have water around, that can protonate the oxygen. And we have the alcohol. In the presence of base, we can do the elimination step. A lot of times you might heat this up to help favor the elimination. But what the base can do, since we have an alpha proton right here, base can take that proton and eliminate. And you're left with an alpha beta unsaturated aldehyde. In problem B, we're using a different base. We're using LDA, which instead of being more of an equilibrium reaction like the one above, this forms 100% enolate. So once you add LDA to this, all of your aldehyde is converted to enolate. From there, now our electrophile is benzaldehyde. That will add. Here's our new bond. And then we get O minus. We still have the phenyl. And I'm going to leave the hydrogen implied. Now you're stuck here until you add water, because you don't have water just floating around in the reaction mixture like we did in A. So now we add water to this. And water can protonate that oxygen. To give you the hydroxide. If you wanted to add base and heat this up, you could do the elimination as well. In C, we have this diethyl malonate reacting in the presence of base with butanol. And now, because we have acidic protons here and here, we have to figure out which ones to choose. And the ones between the 2 carbonyls, those are more acidic. So that's going to be where the base reacts preferentially to give you the enolate. So let's draw that. Just draw the enolate of this in blue to keep track of it. Get the negative charge. Then that reacts with butanol. From here, you can protonate this oxygen. You can do that just from the ethanol. And then, like we did before with the aldol reaction, because we have a base around, you can eliminate the H and the OH to give you a double bond. Like that. In D, we're using methyl lithium, and that is a good nucleophile. So the way you want to think about this is CH3 minus, and the nucleophile can add directly to the aldehyde carbonyl. So we get O minus, we've added the methyl group, and then when you protonate with H plus, that protonates the oxygen. So that would also be the product if you used methyl magnesium bromide. It would be a Grignard reaction. Right, in E, we're doing a reduction with sodium borohydride. So when you reduce an aldehyde or ketone, you end up with the alcohol. So that becomes an OH, and we add a hydrogen to the carbon. Mechanistically, the way you can think about this is just a hydride source adding to the carbonyl. There's O minus. And then in the presence of methanol, we can protonate the oxygen. In F, this is an intermolecular acetal formation. So basically what happens is first you add one of the oxygens to get the hemiacetal. So I'm going to make one red and one blue. So say we end up adding the blue oxygen first. You get this hemiacetal. And then you'll end up losing this OH, and this OH will add to give you the acetal. So in the end, we form this cyclic acetal, which is something we often use to protect aldehydes and ketones. Because if you want to get rid of that and get butanol back out, all you would need to do is add acid and water to hydrolyze that acetal. Right, these next two involve reacting aldehydes with amines, and this reaction also works with ketones. So for just predicting the products, the easiest way, if we have a primary amine, is to think about those two hydrogen and the oxygen going away as water. And then the nitrogen ends up being double bonded to that carbon. This gives us an amine. When we have a secondary amine, we end up with an enamine product. So just to kind of show you how you get to that, similar to the one above, we end up adding the nitrogen, and this actually should only have one hydrogen there. End up getting a double bond to the nitrogen, but now it has two CH3 groups on it. 4 bonds to a nitrogen will have a positive charge. So we're not going to stop there. We need to end up with a neutral product. So what happens is we use one of the protons next to that. This is an iminium ion. And just use a B for a weak base. We'll come and take that proton, push the electrons like this to form a double bond. Now you have this dimethyl enamine. In I, we're doing a harsh oxidation with chromic acid. Because it's a harsh acidic oxidation, that'll oxidize the hydrogen to an OH. So we go from the aldehyde to the carboxylic acid. In J, this is an alpha bromination reaction. Because we're using acidic conditions, we only add one bromine, whereas if we were using basic conditions, both of the alpha hydrogen would be replaced with a bromine. So we just substitute one of those hydrogens. With a bromine, and we're done. K is a Wittig reaction. And in the Wittig reaction, we essentially end up losing the triphenylphosphine and the oxygen to give us a very stable triphenylphosphine oxide. Plus, what we end up with, if I highlight the two carbons that are joining, this carbon of the carbonyl ends up double bonded to this carbon of the ylide. So there's the carbonyl carbon, there is the ylide carbon, and we'll make this a transalkene. And we're first treating this with LDA, which forms the enolate. We only have one enolizable position, so that's our enolate we get. Now, when we react this with iodomethane, this is essentially an SN2 reaction. Or we call this an alkylation. So that attacks the carbon. We lose the leaving group. Here's the product, the methyl added at the alpha position. And in this final product, we're reacting butanol with hydroxide and water. And what you need to keep in mind is you're not going to have just one molecule of butanol reacting. You're going to have many molecules, so you can certainly have two that will come together. This will be an aldol reaction. So we first get our enolate. That will react with a second molecule of the aldehyde. Let's draw it in blue. So one's the nucleophile, and the one in blue is the electrophile. So when that adds, here's our new bond. We get O minus, which I'm going to go ahead and protonate that from the water and make it an OH. And our carbon chain. From here, we still have base around, an alpha proton, so we can just do the elimination. And there's our aldol condensation product.